In this video, we'll learn about the binomial theorem, which is one of the most immediate and useful applications of all of our work with counting. As a quick opening question, consider this interesting pattern that I see with powers of 11. 11 to the 0 is 1, 11 to the first is 11, and so on. And what we see in the answers is Pascal's triangle emerging. The question, does the pattern continue, is pretty easy to answer, because when we consider the fifth case, we find that 11 to the fifth is 161,050. So no, it doesn't. The bigger question, of course, is why does that pattern show up at all? Why did it fall apart in the fifth case? Will it ever work for any other cases? You'll be able to answer these kind of questions by the end of the video. Let's get to the big question. The binomial theorem is all about whether or not you can find a formula for binomial expansion. And here I have the first 5 powers of a binomial a plus b, expanded completely when we collect all the like terms, organized as nice as possible. My question for you is, can you come up with a formula that describes the results that you see in those expansions? Pause the video and see what you can come up with. Here's some observations that I have as I try to generalize for a plus b to the nth power. The first thing I note is that each expansion has n plus 1 terms. When I raise a plus b to the 0 power, I only get 1 term. To the first power, I get 2 terms, a and b. And to the second power, I get a squared, 2ab, and b squared, 3 terms. The next thing I note are that the powers of a are descending. They're counting down. Of course, that's how I organize the terms. But you'll also note that the powers of b are ascending. They're counting up. And as a goes down, b goes up. What's more is if you look at any given term, the sum of the powers of a and b is always equal to n. For example, in this term right here, a is to the second power, and b is to the third power, and 2 plus 3, of course, is equal to 5. Last but not least, the coefficients of every term follow Pascal's triangle, and that means that the coefficients can be found using combinations. When I put all this information together, I have a formula for the binomial expansion. A plus b raised to the nth power. This will be nothing more than the sum from k equals 0 to n of n choose k, there's my binomial coefficient from Pascal's triangle, a to the n minus k, so that the powers of a count down, times b to the k, so the powers of b count up. You'll notice that by starting my lower index at 0 and going up to n, I make sure I have n plus 1 terms. You'll also notice that if you add a's exponent, n minus k, plus b's exponent, k, you get n. And you'll also notice that I'm using n choose k so that I'm always getting the right coefficient from Pascal's triangle. I need the one in row n in position k. Let's see how we can use the binomial theorem to simplify some expressions. If I'm asked to expand and completely simplify a minus b raised to the 4th power, the way I like to do it is think about how similar it is to a plus b to the 4th power. And rather than multiplying a plus b times a plus b times a plus b 4 times, I'll just use what we just learned using binomial expansion. The coefficients of the 4th row of Pascal's triangle are 1, 4, 6, 4, and 1. Meanwhile, the powers of a should be descending. So a to the 4th, a to the 3rd, a to the 2nd, a, and then a to the 0 power. Meanwhile, the coefficients of b should be ascending. So that means I'll have b to the 4th in the last term, b to the 3rd in the second to last, then a b squared, then a b, and then a b to the 0. And since I have a plus b, I'll just fill this with plus signs. Nothing tricky going on here. However, with a minus b, what's going to happen instead is each of those b's I'll have to think of as a negative b, a plus negative b, to correctly use the binomial expansion. And what that means is when I have an odd power of b, I'll get a negative sign. And when I have an even power of b, I'll get a positive sign. And so the expansion would look like this: a to the 4th minus 4a cubed b plus 6a squared b, that was positive because it's a b to the even power, minus 4ab cubed, a negative since the b is to an odd power, plus b to the 4th. And that's all there is to it. Here we look at another example. If we wanted to expand x plus 3y to the 3rd power, the expansion would be a lot like a plus b to the 3rd power. However, the b is 3y, and that coefficient is going to change things a little bit. So when I do my expansion, I start with the coefficients from the 3rd row of Pascal's triangle: 1, 3, 3, 1. And now I need my powers of the first term, x, descending: x cubed, x squared, x, and x to the 0. I'll just write it to illustrate. The second term is 3y. I need powers of 3y ascending. So that means I'll have 3y to the 3rd at the end here. Note the use of parentheses. 3y to the 2nd, 3y to the 1st, and then 3y to the 0. Since I have a plus sign between, I can put plus signs each in between each one of these terms. And then all I need to do is simplify each one of those terms using my rules for exponents, which is relatively easy to do. Note here that you'll get 27xy squared because you'll have a 3, the coefficient from Pascal's, times a 3 squared when you square the 3y, so that's 3 times 9, or 27. And lastly, I also have a 27y cubed, and that's because I have a 3y raised to the 3rd power. In this example, we're asked to find the first 3 terms in the expansion of 2x minus y raised to the 8th power. We're asked to only do the first 3 terms because when you raise 2x minus y to the 8th power, that's going to be 9 different terms, and the problem gets a little tedious. So we're just showing what we know based off the first few terms. I know the first term is going to have a coefficient from Pascal's triangle of 1, but then I'll have to take 2x, the first term in the binomial, and raise it to the 8th power, and multiply by a negative y to the 0 power. The next term is actually going to have something other than a 1 from Pascal's triangle. That's going to be an 8 choose 1 because it's in the 8th row and it's in the 1st position. And then it will have 7 powers of 2x and 1 power of negative y. The third term will be in the 8th row and the 2nd position from Pascal's triangle, and it'll have 2x raised to the 6th and negative y squared. And so we can simplify these first few terms. Let me put a ... to indicate that this would keep going along this pattern. 2 raised to the 8th power is 256. So I'll have 256 x to the 8th times 1, since anything to the 0 power is 1. The next term is going to be negative because of that negative y. Then I'll have 8 times 2 to the 7th. That's the same as 2 to the 3rd times 2 to the 7th. So that's actually a 2 to the 10th, which will be 1024 x to the 7th. This time I'll have a y. The next term will be positive because negative y is being squared. I'll have 8 choose 2, which is 28 times 2 to the 6th. Now, 28 times 2 to the 6th is 28 times 64, and that's 1,792. So I'll have 1,792 x to the 6th y squared. The next term will be negative, and it'll keep going along like that. We worked out the first 3. In this example, you can see how things might start to get a little bit tricky. because we're asked to expand x squared minus 2x raised to the 10th power. Not only do I have a minus sign and a coefficient of 2 on the second term, but both the first term and the second term have expressions of x. So we should be very careful here about the first 4 terms. Generally speaking, the first 4 terms in the expansion of any binomial, a plus b to the nth power, are always going to look like n choose 0, a to the n, plus n choose 1, a to the n minus 1, b, plus n choose 2, a to the n minus 2, b squared, and then the fourth term will be n choose 3, a to the n minus 3, b cubed. So when I write that out here, I'll get 10 choose 0, x squared to the 10th, plus 10 choose 1, x squared to the 9th, times negative 2x to the 1st, plus 10 choose 2 times x squared to the 8th, times negative 2x squared, plus a 10 choose 3 times x squared to the 7th, times negative 2x to the 3rd. As we go through and simplify, 10 choose 0 is the same as anything choose 0, that's 1. X squared to the 10th is x to the 20th, and there's my first term. My second term is negative because of the minus 2x. 10 choose 1 is 10. X squared to the 9th is x to the 18th. There's a negative 2 there. Negative 2 times the 10 makes a negative 20. And the total number of powers of x's that I have is x to the 19th. X to the 2nd to the 9th plus an extra power of x right here. My next term is positive because the negative 2 is being squared. I have 10 choose 2, which is 45. And then I have x squared to the 8th, which is x to the 16th. Then I have 2 more powers of x at the end, and multiplied by a negative 2 squared, which is a positive 4. So 45 times 4, that's going to give me a 180. And when I put the powers of x's together, I get x to the 18th. My next term, once again, is negative. This time I've got 10 choose 3. 10 choose 3 is 120. Then I have x to the 2nd to the 7th power, which is x to the 14th, multiplied by a negative 2 cubed. Negative 2 cubed is negative 8. And negative 8 times 120 is negative 960. And so my fourth term in this expansion is minus 960. And you'll note when I put the exponents together, I get x to the 17th. And it continues just like that. Okay, that's enough expanding. Let's see if we can use what we know about expanding binomials to find the coefficient of a particular term in the expansion. Let's see if we can do it without expanding the entire thing. Pause the video and see if you can figure out what the coefficient of the x to the 8th y squared term would be in the expansion of x plus 2y raised to the 10th power. One way to solve this problem would be to notice that we're looking for the third term in this expansion. That's because when I look solely at the variable parts, I know that the first term is going to have an x to the 10th. The second term is going to have an x to the 9th and a y to the 1st. And then the next term is going to be an x to the 8th and a y squared. Of course, the coefficients here might be something different, but I know which term I'm looking for now. And it's also important to notice that when we're talking about the third term, we're saying k equals 2 in the formula. And so the coefficient of the x to the 8th y to the 2nd term can be found by doing 10 choose 2, and I'm going to keep the x in here for now. That would be x to the 8th and 2y, I'll keep the y in as well, to the 2nd power. Okay, now 10 choose 2 is 45. So I'll have 45x to the 8th, and 2y to the 2nd power is going to be 4y squared. Oh, and now I can see that my coefficient is going to be 180. That's how many x to the 8th y squareds I'll have. And that wraps up this video. The binomial theorem can efficiently expand any binomial, and the combinations from Pascal's triangle play a big role.